All right, let's dive into something that sounds, well, pretty much impossible. Today, we're going to untangle how companies can analyze each other's most sensitive data without ever actually having to share it. We're talking about the powerful tech that really makes data clean rooms work.
So here's the central puzzle, right? How can two different companies get valuable insights from their combined data when they legally or just practically can't share it? I mean, think about it. You've got an advertiser with all the sales data and a publisher with all the ad viewing data. They need to connect the dots, but just sending over a spreadsheet of user info? No way. That's a privacy nightmare and a business risk. So how do you make this impossible collaboration possible?
Well, the answer is something called a data clean room. And the best way to picture it is like a digital Switzerland, this perfectly neutral, super secure space. Both companies can put their data inside, and it can be analyzed together. But here's the most important rule of the clean room. The raw individual level data never, ever leaves. The only thing that comes out is aggregated, anonymized insights. Nobody gets to peek at the other team's cards. Okay, so how on earth does that actually happen? Because it's not just a fancy, locked-down database. Not at all. Real data clean rooms are powered by some seriously advanced cryptographic and hardware-based technologies. So let's pop the hood and take a look at the privacy engines that make this whole thing run. First up, we've got something called Secure Multi-Party Computation, or MPC for short. And honestly, the best way to think about MPC is as a cryptographic fortress. The whole point is to let a group of people or companies do math on their secret data together, but without anyone ever having to reveal what their secret data actually is. So how does it do that? It's pretty wild. Imagine you have a secret number. Instead of sharing that number, you use cryptography to split it into a bunch of gibberish-looking pieces, or shares. Each share is totally useless on its own. But, and this is the magic trick, the math is set up so that your gibberish shares can be combined with someone else's gibberish shares to compute a result, like a sum or an average. Only when that final result is reconstructed does the meaningful answer appear, all without anyone ever seeing the other's original secret number. The inputs stay completely private. All right, our second engine takes a totally different path. It's called a Trusted Execution Environment, or a TEE. Now, if NPC was a fortress built out of pure math, a TEE is more like a physical, tamper-proof vault that's built right into the computer's processor chip itself. Here's how TEEs work. They use a special, walled-off section of the CPU that's called an enclave. All the sensitive data goes into this enclave while it's still encrypted. It's only decrypted for the split second it's being processed inside that secure hardware vault, and then the result is encrypted again before it comes out. And this is the part that's really mind-blowing. Not even the owner of the machine, like the cloud provider running the server, can see what's happening inside that enclave. It's a true black box. Okay, let's pause for a second because this is a really important distinction. Both MPC and TEEs, they have one job: protecting the data while it's being used. They're making sure nobody, not your collaborator, not the cleanroom operator, can see the raw data during the actual computation. But that's only half the battle. What about protecting the result of that computation? For that, we need a completely different tool. And that's where our third piece of tech comes into play: differential privacy. If MPC is a fortress and TEEs are a vault, think of differential privacy as a kind of protective invisibility cloak for the people inside the dataset. Its one and only job is to make sure the final answer doesn't give away too much about any single person. So what does that actually mean? Well, differential privacy gives you a powerful mathematical guarantee. It promises that the answer to any query, say, how many people bought our product, will look almost exactly the same whether your personal data was included in that calculation or not. In other words, it makes you statistically invisible. And how does it pull off this magic trick? It's actually pretty clever. The system takes the perfectly true answer and adds a tiny, carefully calculated amount of random statistical noise. This makes the final number just a little bit fuzzy. Not enough to make it useless, but just enough to protect the privacy of any one person whose data was part of the calculation. So there you have it. We've got these incredible tools: MPC, TOEs, and differential privacy. But here's the thing. You can't just pick one and say it's the best. Choosing the right approach is all about understanding and navigating some really big trade-offs. Let's break that down. You go with MPC, you get this amazing, mathematically provable privacy without having to trust any hardware. The price you pay? Speed. It can be anywhere from 100 to 10,000 times slower than a normal computation. Whoa. On the other hand, TEs are lightning fast, almost as fast as regular computing. The trade-off there? You have to place your trust in the chip maker, and you have to be mindful of some potential vulnerabilities called side-channel attacks. And then there's differential privacy. Its trade-off is right there in the open. The more privacy you want, meaning the more noise you add, the less accurate your data becomes. It's a constant balancing act. And these trade-offs, they lead us straight into the messy realities of using this stuff in the real world. It's one thing to talk about the theory, but it's another to actually manage the risks and the budgets involved. One of the most important concepts to grasp, especially with differential privacy, is the idea of a privacy budget. You see, you can't just ask an endless number of questions about a dataset. Why not? Because every single answer, even with that fuzzy noise added, leaks a tiny, tiny bit of information. So think of it like a privacy bank account. Every time an analyst runs a query, they spend a little bit of that budget. And once the account is empty, that's it. No more queries allowed. This is a super important safeguard to prevent what experts call a death by 1,000 queries, where someone could slowly but surely erode privacy by asking question after question after question. Now, this whole trade-off is captured by a single Greek letter, epsilon. And it really boils down to this. A low epsilon means you're adding a lot of noise. That gives you really strong privacy, but the data is less useful, less accurate. A high epsilon means you're adding very little noise. You get beautiful, accurate data, but the privacy protections are much weaker. And finding that just right epsilon, well, that's the million-dollar question. But even with all of these safeguards in place, the budget, the noise, there's still one big risk we have to talk about. And that's the risk of a clever analyst trying to re-identify people by asking a series of very specific, very sneaky questions. Here's a classic example of how that could happen. It's called a differencing attack. First, the analyst asks, how many users in all of California converted? The system answers, 1,050. Okay. Next, they ask a slightly different question. How many users in California converted? But let's exclude everyone in the 90210 zip code. The system answers, 1,049. And just like that, game over. By subtracting the two numbers, the analyst knows with absolute certainty that exactly one person in that specific zip code converted. That is a huge privacy breach. So how do we stop that from happening? Well, modern clean rooms have built-in defenses. First, enforcing that strict privacy budget helps a lot. They also have systems that can analyze patterns of queries to spot this kind of suspicious behavior. But maybe the most important defense is this. The system will just flat out refuse to answer any query if the group of people in the result is too small. It's a simple, powerful rule that prevents anyone from being isolated and singled out. And all of this really brings us to the fundamental tension at the heart of our digital world. We've got these incredible technologies designed to walk a tightrope between two powerful competing demands, the need for maximum data utility on one side and the non-negotiable right to privacy on the other. As we move forward, that push and pull is only going to get more intense, and it leaves us with a really big question. In a world that demands both, which one will we ultimately be forced to trade?